Hello everyone, a very good morning to all the students who are present in today's lecture of digital communication. I hope my voice is properly audible.
Yes, sir.
Thank you Nachiket for the response. So uh, today and tomorrow's lecture kind of we dedicate to uh, revision, query solving, and covering up I think one or two topics which are remaining there for our unit. Next week we will have internal assessment. So I think it is on 15th or 16th. Which date it is? Do you remember the timetable? Okay. So our
15th.
digital, yeah, 15th. So our digital communication is on 15th of September and 9:30 to 11 a.m. Time period, time duration. And I also believe that you all have been informed about the uh, the format of the paper, the question, number of questions, marks, etc. Yes. Yes or no? Okay, I believe
What, sir? Sorry.
the duration and the format of the paper, which platform it will be conducted, all these information, I hope it is with you people.
Okay. Yeah.
Hannah? Yes.
Yeah, like except for the format, proper format, we have everything else.
Okay, so it will be conducted on Teams and it will be of
Yeah.
90 minutes duration, and it will be of you have to upload your response like that. Okay, it will be, you need to write in your hand written and then scan and then upload. So the same like how you were earlier done, but more you can say formalize the semester. So my sincere advice to all of you, since this is our 16th lecture today, so almost 15 lectures video recording, except one, there was some issue with the cloud. Except one lecture, all the recordings, they are available with you. Anyhow, in that, in case if you feel you have low data bandwidth to download the videos, stream the videos, side by side I've also uploaded the PDFs which we referred while going through those lectures. So both the PDFs as well as video recordings are with you people, and ideally you should go and listen to video recordings also, because not everything we discuss in class they are exactly written in the PDF, because we discuss, we elaborate, we elongate whatever statement is written. So to get the complete discussion, it is ideal to listen to the videos and make your own points, make your own notes, isn't it? Okay, I believe you all agree with this. So let me share my screen. Is the screen visible? Students, is the screen visible?
Yes, sir.
Yes, sir.
Okay. So earlier we have seen these modulators, demodulator, QPSK, BPSK, MREPSK, and then we finally reached this slide, and for further improvement we discussed that we need to combine different schemes. So we just, I think, kick-started this topic in the last part of our last session, the combination of M-array PSK with ASK. That is nothing but your QAM, quadrature amplitude modulation. You all agree? I think we reached till this slide. If you haven't revised the topics, please do so, because next week you will have, internal assessments. So you will also need some time to go through the topics once again, and to understand is very important, because questions, it will not be like very simple or straightforward. Though I'm not saying it will be difficult, but it will definitely require a very in-depth understanding of the topics. Okay. So quadrature amplitude modulation involves splitting the signal into different phases, and each phase is having a different amplitude. So here you can see earlier, if you remember the QPSK, like this. Okay, we were dividing into different parts, and we were having a constellation diagram where 4 points were there. I think it is not there in the slide, but I drew it on these sketch pads. I remember that. Okay, so I will share those written notes also in PDF form in the Teams. Okay, all the handwritten thing which we have done on sketch pads, that also you will be getting. No issues with that. So don't worry that can get a ready reference for that. So if in QPSK we use 2 different amplitudes. So in QPSK, how many phases are there? 4 phases. Okay, and each phase, if you are representing with 2 different amplitudes, so how many? 8. How many combinations are there? 8 different combinations of phase and amplitude. So we call it as a 8 QAM. Okay, so for 8 QAM, you have 8 combinations, so you can 3-bit modulation simultaneously. Here 3 bits are modulated simultaneously. Now different forms of QAM are available, and they are known as 16 QAM, 13 QAM, 64, 128, 256 QAM. So if I say 64 QAM, what do you understand? If I say 64 QAM, what do you understand? How many phases and how many amplitude levels can be there? Is it 32 phases, 2 amplitudes each phase? Or is it 4 amplitude levels, 16 phases, etc.? Okay, so that question I leave to you to find out, and then we'll discuss tomorrow. Okay. So are we good, students?
So,
Hanji. Yes. Somebody said yes, sir, or some question is there?
yes, sir. I said
Okay.
yes.
Okay. So this is the QAM modulator. So not very different from a QPSK modulator. We were where we were splitting the incoming bit stream, and then we were multiplying it with a certain carrier with 90-degree phase shift and without 90-degree phase shift, and then linearly summing up. In this case, we have a arrangement so that we make use of the levels, right? We want levels because amplitude is also there. So here you can see input data is empty. It is coming at a bit rate RB, and bit splitter, it is dividing it into Q, I, C. So this C is controlling this 2 to 4 level converter of this Q and I channel. And essentially we are getting a pulse amplitude modulated wave. Okay. This we are feeding, and the rest of the concept is known to you. So the 2 to 4 level converter essentially brings different amplitude levels in the output. So as you can see, I and Q, these I or Q values, they are written here, and depending on the value of the C bit, you have an output corresponding for that value of C and I or Q combination. So it is minus 0.45, 0.4541, minus 1.3, like that. So different values of amplitude you are getting at the output. So for 4 phases and 2 amplitudes, you have 8 combinations. We're calling it as 8 QAM. So if you look at this 8 QAM constellation diagram, basis of on the basis of your IQC combination, so 3 bits are there, so total 8 possible combinations are there, right from 000 to 111, and the signal value ST is of this form. So essentially you have a different amplitude and a different phase. This represents your 135 degree, this represents your 45 degree, this is your 90 degree sorry, this is your 180, this is 0, and this is minus 45, this is minus 135, like that. Sorry. So you can see 000 amplitude is 0.765 and phase angle is 135. So this is 000. So the location of this constellation point in this constellation diagram, in this phasor diagram of this 000. So whenever a 000 3-bit input will come, the output will have this value. Output will have this phase, this signal, 0.765 cos omega ct plus 135. And likewise for different combinations of bit. So are we good, students? Are you able to appreciate the location of different phases along with different angles?
How do we get these values, sir?
This is on the basis of this output, okay, which is coming from the 2 to 4 level converter. Product modulator will give you, different phases. This is responsible for the phase thing, and this is responsible for the amplitude. Okay. So we are looking at from a block level. We are not going to discuss the electronic circuit for that or digital circuit for that matters. But essentially, this math has to be understood. When we say acha, and you can see what are the very common product which we are using on the basis of these digital modulation, DTH. You can go and search the DTH and all these because a huge amount of data is required to be transmitted using the digital communication for DTH. And we are seeing videos, right? We are seeing live matches. So live streaming of your match, so it is essentially video. So high bandwidth is required, and from where you will get high bandwidth? Only because with the help of lots of possible ways through which you can modulate your data, modulate your input data. So in this case, you can see 3 bits at a time you are able to modulate, and you have these many combinations, 8 combinations. Okay, so you can send data at a very fast rate, and so I advise you all to search for this DTH thing. No, what are the modulation schemes it is following? What is the bit rate? And all those details I will discuss tomorrow, definitely. Okay. So this is about 8 QAM, and if you look at the constellation diagram for 16 QAM, 32 QAM, 64 QAM, so you can see how many different phases are there in each angle. At each angle like this, you will have different values. We are not I'm not asking you to memorize this, but at least understand this 8 QAM. Okay, and because it will go till 256 QAM, 128 QAM essentially. Okay, so everyone is clear with this QAM till QAM MRE PSK with amplitude modulation. Now you all have to start revising your content. Okay, otherwise it will be very difficult in the last moment to revise. So say as the directions are there, there will not be any classes during your regular classes during your internal assessment week. I hope this message is also reached to you. Okay, so I believe you're all aware of that. So essentially tomorrow is the last lecture before internal assessment, and let me share now different. As I promised that we will quickly go through the some basic concepts kind of thing. So yeah. Yeah, you all can see this screen. Is the screen?
Yes, sir.
Okay, thank you. And so this much of this portion we have seen already. What is communication? What is noise? What is distortion? I think these few of these slides I incorporated when we were starting our initial introduction lectures. And transmitter, communication channels, and what type of different communication channels are there. This we have discussed, so I'm quickly skipping it. We'll stop there wherever I think we need some little brush up. Okay, attenuation and noise, attenuation and distortion. What is the difference? Then the simplex, half duplex, full duplex, half duplex, full duplex types of communication, baseband and broadband transmission, and AM amplitude modulation. Then this FM and PM we discussed. I remember this diagram. We have discussed this in our regular lectures. And then this modulation and demodulation schemes. What are the different electromagnetic spectrum we are using? And essentially, if not all, but at least few of the frequency ranges we should always remember, like VHF and UHF. They are heavily used in modern day products, modern day systems. As you can see, this is, if you consider VHF, UHF together, it is actually ranging from 30 megahertz to 3 gigahertz, and most of the devices, they are working into this range, VHF to UHF, right? So I mean, this is a very important frequency range spectrum, part of a spectrum, and majority of our products, they are lying into this range. VHF and UHF, very important. But with 5G, we will go with this, SHF and EHF. It will go in several tens of gigahertz, right? So the quantum will shift from VHF, UHF to EHF, extremely high frequencies. Anyhow, that's a matter of future. And these applications, amplitude modulation, we have discussed very detailed. I'm skipping this. Then sidebands also. I think these all topics, like the total power in DSB, amplitude modulated, double sideband amplitude modulated, is the sum of the sideband powers plus the carrier power, and this is a calculation for that. And we get this formula, right? PT is PC1 plus m square by 2. I hope you all recollect this formula. We have to remember. Yes or no?
Yes.
Hello. And this is use of a product modulator, analog multiplier, and how you're able to get the double sideband modulated signal. And in time domain, how you generate with the help of voltage divider circuit, a kind of effect of that. And if you look at the amplitude modulation in I think I have shared this slide with you people. I have not shared, then I'll share with you. So essentially, your voltage and current relationship or amplitude modulation generation is in a way, two ways. It is a square law response, or it is a linear voltage current relationship. So we can also generate our modulated signal, AM modulated signal, with the help of product of carrier and modulating signal. So essentially we go for your non-linear component or circuit square law function. So what is that device, square law function? So is a diode. Diode, if you look at this, it is resembling with the response, the VI response curve of the diode, right? Forward bias condition. Yes or no? Yes. So we make use of diode for having that non-linear parabolic response, and we make use because there is a square law function that varies in proportion to the square of the input signal. So BJT FETs, they are also used, but the majority is a diode which is used. So essentially it is not only the non-linear square law, but a portion of your this AV means a 1th power of this V also comes. So ideally it is I equal to BV square, but practically it is some portion is there for the linear component also, and we need to have this understanding in our circuit also. So this is the circuit where we are using a diode. This is our carrier, this is our modulating signal, and we are getting an output voltage. So to produce and read modulation, the carrier and modulating signals are added and applied to the nonlinear device, which is the diode. And there is some calculation I think you all might have gone through. And when you solve this calculation, I'll share this PDF. Because of the time restriction, we are not going line by line, but it is a simple thing. You can go through total V we are applying to diode is VC plus VM, and then use the relationship what we are following, I equal to AV plus BV square for this circuit. So you feed the value of V and then you expand, you will get these many considering a trigonometric function for VC, you will get this expansion. So essentially the output will consist of carrier, will consist of the modulating signal, harmonics of carrier, the carrier modulating multiplications and harmonics of the modulating signal with the different powers of the input modulating signal, like VM square here. So modulating signal and harmonics which are there, these are unwanted. You can easily get rid of it by filtering it. So you can use as a band pass filter. For band pass filter, you can use a LC tank circuit. I hope you all have seen at some point of time resonant circuit. Yes or no?
Yes, sir.
So the resonant circuit is kept at having a resonance frequency which is equal to carrier frequency. So maximum energy dissipation will occur across output at that particular frequency FC, and there will be a response to a certain level till FC minus FM, and at this side and FC plus FM. So that minimum and maximum value is there. So circuit is resonant at the carrier frequency and has a bandwidth with wide enough to pass the sideband. So bandwidth is essentially the response is so that it covers the two components, the two sidebands. The next is your demodulation part. And I also believe in your course you might have gone through vestigial sideband, VSB. Yes? Yes or no?
Yes, sir.
So why we require vestigial sideband? Because when it comes to a single sideband, it puts a lot of constraint on filter design. Filter design essentially are techniques with you design a circuit, you have the values of the components. If it is an analog filter, if it is a digital filter, you are finding the coefficient values. Again, they are representing storage, bit storage, and you store those coefficient values. So you can go for a steep transition from passband to stopband, but at the cost of ripples in the stopband and the passband. You all agree? I repeat, if you have two sidebands, you have carrier, right? You decided that I will not send one sideband, and you need some filter. Now the filter should have good quality, good response, means it should completely eliminate the portion of frequency which you don't want to get it transmitted. Now because of the real time performance, because of the practicality, it is not a straight line, vertical line. It is actually a gradually decreasing response of the filter to the frequency. So some portion is getting passed. But if you try to make it steeper, the transition from the pass band to the stop band, ripples will come in pass band and stop band. Now, why ripples are not good? If I'm saying there are ripples in pass band and stop band, can you recollect why ripples are not good?
The ripples are not good because they distort, like, they don't give a proper value.
Yes, ripples are not good because ideally in stop bands, so we take one by one, stop band and pass band, which is severe, right? If you take first stop band, ripples in stop band will pass on the unwanted frequency spectrum into your main signal, the output signal of the filter. It may lead to distortion. At the same time, ripples in the pass band will result into unequal response to different frequencies. Again, it is leading to distortion. Though this distortion is not that much severe, but still it amounts to a little distortion and also noise. So ripples there have to be avoided. If you are going for less ripples in pass band, stop band, then what will happen? The transition from pass band to stop band, the slope will be very less. It will be very not a narrow slope, but it will be wider slope. What will happen in that case? Unwanted frequency component will get a peak into your past signal. So there is a trade-off, always a trade-off between the slope and the ripples which are there in your filter design. So vestigial sideband we make use, we allow actually to pass a portion of your suppressed sidebands. It can be LSB, or it can be upper sideband, or it can be lower sideband. So hence simplifying the design. So we do not have stringent conditions over our filter design, and we can have a moderate filter, and we are okay with some portion of sideband to be passed, that we call as vestigial sideband. So it is appropriate for signals that have a strong low frequency component, such as video signals. So video signals earlier, they had a strong VSB participation, VSB modulation. So this is a generation of vestigial sideband. You can see a small portion is of the LSB part is allowed to pass. This is FC and this is towards the LSB part. Okay, we are calling it as FV. Anyhow, so AM demodulation, we know we have discussed in certain detectors, synchronous detection. We have seen a lot of coherent detectors, diode detectors. So let's go through it. So this is a diode detector. Just now we have seen why we are using diode detectors. Can somebody answer? Just now, few slides ahead ago, we have seen because of the yes. Anyone can answer? Because of the characteristics of the diode, because of the VI characteristics, isn't it? Please speak up, students. Or let me take attendance. Okay, so Adit Patel, are you there? Anshul Patel, can you listen? Aryan Pandya. Bhargav Ghilani. I hope you all have joined this class and be there. Huh? Hirva Patel. Jash Dalal. Jeet, can you listen? Jeet Davda. Kshitij Surana, can you listen? Krisha Solanki. None of these students will take name, they are responding. I hope they are properly connected. Mihir Shah. Neil Lakum. Am I audible?
Yes, sir, you are audible.
Okay, because none of the students they are responding, I seriously doubt whether I am audible or not. Rishit Samaria. Because it is time to wake up. Your assessment is coming. Ideally, you should be there in class. Trushil. I see. This is not good. It should be there. Okay, one more important thing is before we complete, just to remind you, deadline is tomorrow for that PDF submission. One lab assignment 1 and lab assignment 2. Don't send assignments over email. I will not accept, because last time also my email got flooded because many students they claiming that they missed this deadline. So a lot of time is there, considerable time is there. Don't decide to submit in the last moment. If the 5 p.m. is the deadline, don't go for 5:1, 5:2, 5:3. You can upload a few hours earlier than the deadline.
Sir, last time you by mistake trim hello. Sir, form was editable.
Yes, I remember, because actually what happens, because of my teams got updated na. So earlier that assignment option was coming in the teams
Students could edit the form.
So this time it is,
that was causing the problem.
yes, this time it is not there. Nobody can edit. That's why I I am forcing you to upload the PDF once again, and it is mandatory question, so you cannot press the submit button unless you submit both the PDFs. Be careful in submitting both, and don't go for in a hurry. And this will be part of your continuous evaluation. Remember, take it seriously. If you not submit, you will get 0 in that part. That is for sure. You submit, qualitatively you will get some marks. So please do remind. Okay, we go back to the revision. Hanch.
Sir, what we have to do in SSB, that you have given the code, so we are not getting it. So
Sorry,
can
you
you
are not.
please, sir?
Sorry?
Am I audible right now?
Ha.
Sir, what we have to do in SSB experiment? The
So
part 2 of.
I have
Yes, you
shared
have shared
filter wala
the.
code na?
Yes, sir.
So you
But
have to filter. You have to filter the either of the USB or LSB, lower sideband or upper sideband.
Sir, how can you please explain? Means
That
can you show
that you
some
have to
demo,
explore.
please?
So okay, I'll explain you. The filter which you are seeing, the code which I have shared is a digital filter. Now, what is the difference between the concept of frequency in analog domain and in digital domain? Can somebody tell me? Can you tell me? Once again, the difference between the concept of frequency in digital domain and in analog domain. Do you recollect?
That is discrete and continuous something.
Not discrete. See, the biggest difference is, the only biggest difference is your frequency in analog domain or continuous domain, you can say, is hertz, whereas in digital domain, digital frequency is normalized frequency. What is normalized frequency? It does not have any unit. It depends on the sampling frequency. And why sampling frequency is coming into picture? Because while going from analog domain to digital domain, continuous to digital domain, you are sampling at a certain rate, right? So your FC, the carrier frequency, and the sampling frequency, Fs, if you take the ratio of this Fc by Fs, you will get a normalized value, and that is nothing but your normalized frequency. Got it? That is the difference between the concept of frequency in digital and the analog domain. In digital domain, you have a normalized frequency. Now, coming back to the question which Achal, I think, asked me. So there you can see filter is designed, some value is written 0.2, 0.3. What is that? That is the normalized frequency value. So if you want to design a filter at particular frequency, say FC1 or F1, how will you find the cutoff frequency? What number value you will write? It depends on the sampling frequency. So if suppose your sampling frequency is say 1 kilohertz and you want to design a filter with a cutoff frequency of say 500 hertz. What is the ratio? 500 hertz divided by 1 kilohertz. Achal?
Yes, sir.
अरे आप सुने अभी जो हम आपको कहे? You have understood difference between digital frequency and analog frequency? Yes or no? I can explain once again, no problem. Don't worry.
सर थोड़ा समझ में आया.
अच्छा थोड़ा कोई बात नहीं. So see, when we say we are designing an analog filter, cutoff frequency is straightforward hertz, right? 500 hertz cutoff frequency, 1 kilohertz cutoff frequency, like that. But in digital filters, we do not have this concept of hertz. We make use of these values of the frequencies, but essentially we are using normalized frequency. Why normalized frequency? Because in digital domain we are sampling the signals, right? We are sampling at a rate fs. So instead of having a frequency value stated as the cutoff frequency value, we mention the normalized frequency. Okay, so if you are designing a digital filter with certain frequency values, you will feed normalized frequency value into the equation, and that's what you are looking into that function, that IIR function, right? You are feeding 0.2, 0.3, something like that. From where that 0.2, 0.3 has come, it is the ratio of the cutoff frequency with the sampling frequency. Now got it, Achal?
Yes, sir.
So when we are talking of digital sampling, when we are talking of sampling, there will be a sampling rate. So all the frequencies, they are with reference to sampling frequency. So if I say I design a digital filter of a cutoff frequency 1 kilohertz, right? So you need to look upon what is my sampling frequency. If your sampling frequency is 2 kilohertz, take the ratio 1 kilohertz by 2 kilohertz. It will come around 0.5. So your normalized frequency value in that case will be 0.5. This value you will be using to feed it into your filter design. So if I say now you have to design a filter with a particular frequency which is USB, means upper sideband. Upper sideband is FC plus FM. Let us represent this value as FUSB. So you are supposed to design a filter at FUSB. So what will be the normalized frequency value? FUSB upon FS, sampling frequency. Now got it?
Oh, okay, sir.
You try or I mean, once again, we can take this, but I want you people to do it because you are supposed to already do it in 2 semesters ago. That is the thing. So if you will do it now, you will have greater confidence. Code I have already shared. That is for IIR filter design. And I hope you recollect FIR filters and IIR filters, right? So like IIR function is there in Scilab or MATLAB. Similarly, FIR function is also there. You find out the coefficient values, no, H0, H1, H2 based on the order of the filter. How big is the order, that those many coefficient values will be there. So I think definitely you will remember, oh yes, some sort of this we studied. Just a little brush up you will require. And in the end, I am always there to help you out. Say something.
Yeah, okay, sir.
I mean, to everyone. I'm not, specifically asking from Achal. If anyone has to add to it, say something. Okay, so I think we reached. So one way is here, the response of the diode is similar with how is expected. Synchronous detection, we make use of the carrier signal, the same clock frequency, and we get our original signal back. And we have seen AC sine omega ct, you multiply again with the sine omega ct, you will get AC sine square omega ct. Sine square omega ct, you can like sine square theta. What is the formula? 1 plus cos 2 theta, right? So you write it in that form. You make use of a band pass filter, you get rid of it. So that is nothing but your synchronous detection, right? So you are multiplying with the same carrier of the clock signal at the receiving end to get back the original signal like this. So this is what is shown. If you are receiving a USB upper sideband single sideband signal, you are multiplying with the carrier, you are getting its components. You can use low pass filter to get back original modulating signals, right? And this is represented like this. I think we pretty much covered our few topics fast, and we'll meet tomorrow morning 11 a.m. once again. If any query, anything is there, please discuss. Otherwise, we are good to end this session. If you have anything to say, please feel free. You're all getting along nicely with the flow of digital communication. Yes or no, Shailesh?
Yes, sir.
Thank you, Achal. And Shailesh left. Harshil? Shivam? Okay. With if no further queries here, thank you everyone.